Hello, everyone. We have been studying rotation for quite a while now, and we've gone through pretty much all of our models that we developed for linear motion, with one exception, right? And that is momentum. Hopefully you remember that the linear momentum, which is denoted for some reason by a p, right, is the mass times the velocity of an object. Right? That is its momentum. You might remember that we use momentum most usefully to analyze collisions. The units, of course, for linear momentum come right from the equation. Mass would be in kilograms, velocity in meters per second, so it's a kilogram meter per second. There's no fancy name, there's no derived unit for momentum. They just use those units, kilogram meters per second. Well, there is a quantity that we can use when things are rotating called angular momentum. Okay? It is denoted by an L. In this case, I'm going to use a capital L because we are going to begin today by talking about the rotational inertia the angular momentum of a rigid object rotating about a fixed axis. And usually that's denoted with a capital L. Right? Sometimes they use lowercase l's, but I'll show you that in a little bit. Now, I'm not going to do a big derivation here or a lot of hand waving. Basically, at this point, I hope you realize that in most cases, you can kind of map the linear quantity over to the angular quantity, right? And we're going to do that here. So linear momentum is mass times velocity. Angular momentum is, well, what's the rotational analogy to mass? It's, of course, rotational inertia, right? Capital I. And what's the rotational version of velocity? It's the angular velocity. So you might not be too shocked to find out that the angular momentum of a rigid object rotating about a fixed axis is simply I omega. Rotational inertia times the angular velocity. And of course, anytime you see rotational inertia, all of the things that we learned about it and all the different specific rotational inertias of various continuous objects around various axes, right, could apply to find an object's angular momentum. Sorry, just the way it works. Everything's a little harder in rotation. Units, well, again, from the math model, rotational inertia, which is the sum of all of the mr squareds, right, is kilogram meter squared. Right, r squareds are meter squared. Angular velocity is, of course, radians per second. So you put that together, and the radian drops out because it's a name more than it's a unit. So the units for angular momentum are kilogram meters squared per second. Again, no special name for this. No special name for this. It's not a Newton. That's a kilogram meter per second squared. This is a kilogram meter squared per second. Right, so this is just what it is, all right? For whatever reason, just like they do with linear momentum, that they didn't give it a special name, they didn't give the angular momentum units a special name either. It's just a kilogram meter squared per second. Angular momentum, like all rotational quantities, is a vector, but you rotate around the vector. So we use our old friend, the right-hand rule. Right? You put the fingers of your right hand in the direction of rotation. The vector acts in the direction of your outstretched thumb. So counterclockwise, hopefully you're doing this right now with your hand, right? Your thumb points out, which is positive. Clockwise, your thumb points in, which is negative. So it follows all of the rules that we learned for torque and angular velocities and angular accelerations and all those other things, right? Counterclockwise ends up being positive and clockwise is negative. So let's do a little problem with this. Why is this called example number 3? I have no idea. Just go with it. So we have 3 particles. All of them are the same mass, m, and m. They are fastened together and to an axis of rotation here at O, all right, so they rotate around this point, by 3 massless strings, each with a length little l. So that's L, and that's L. The combination rotates around that axis with an angular velocity omega in some amazing way where this orientation stays this way as it rotates. So it's going along counterclockwise, right, as you see in the picture, but it stays in a nice straight line. That would be a tricky thing to actually set up in real life, but hey. I want all of my answers to be in terms of m, little l, omega, and relative to the point O. You're going to notice that in these angular momentum problems, it's always important to understand where your axis of rotation is. All right, it's all relative to a particular axis, just like it is with torques. Okay. So first thing I want to know is the rotational inertia of this combo. Certainly, we did not have this combo as one of our, ones that we derived. But I hope you're looking at it and saying, well, it's not really that bad, right? I mean, really, it's 3 particles. These strings don't count because they're massless. We'll talk about what happens if they're not massless in a moment, but since they're massless, really doesn't this just act like 3 particles? And the rotational inertia of 3 particles would simply be the sum from I equals 1 to 3, because there's 3 particles, of all of the mi ri squareds. If we expand that out, right, that would be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. But let's take this one at a time. This mass, this one, the inner one here, which is a mass of m, is how far away from the axis? L. So its rotational inertia will just be m L squared. What about this middle one? Well, it's got a mass of m, but it is 2L away. So it would be m times 2L squared. And this third one, the outer one, it's also got a mass of little m, but it's 1, 2, 3L away from the axis. So this would be m times 3L squared. You see how I'm breaking this up into 3 particles, which are each a different distance from the axis of rotation? Do the math. You get ml squared plus 4ml squared plus 9ml squared for a grand total of 14ml squared. If we knew what m and l was, right, we'd be done. Does this one make sense? Common technique, you break it up into pieces if you can, right? Unless it's one of the ones that we had to derive in class. Now, what if these were thin rods of some mass and a length L? Okay, well, then they would contribute to the rotational inertia. So we would have to add to this 14ml squared, which would still be the same for the 3 masses, some rotational inertia for these 3 rods. Now, there's 2 ways to do this, okay? And I want to do the easy way, or at least talk through the easy way, which would be instead of dealing with them as 3 separate rods, okay, which would get tough because while this rod is rotated about one end, and we already have a formula for that, this rod is rotated about that point. Not about the end of it, which would be here, but around that point. And this rod is also rotated all the way over here. Now, we could figure that out by applying the parallel axis theorem to this rod and that rod, but there's an easier way to do this, which is, why not just treat it like one long rod of length 3L and total mass, whatever the 3 masses are, to add it up. And then we could plug it into the rotational inertia we derived in class of one long thin rod rotated about one end. See what I'm saying? So if they want to make it easy, they might make these massless strings, right? Which they somehow managed to get to rotate in this straight line pattern. But if they wanted to make them thin rods, which might be another way they go, really doesn't make it that much more difficult. You would just add that on. Treat it as one long thin rod. Okay? So in part B, let's find the angular momentum of the middle particle, just the middle particle. Well, let's treat the middle particle at this point as a rigid object rotating about a fixed axis. It's legitimate in this case because it's part of a rigid object rotating about a fixed axis. In which case its its angular momentum would be its rotational inertia times omega. And didn't we already figure out the rotational inertia of this point, right? It's m times 2L squared or 4ml squared. So we plug that in. That's the angular momentum around that point of the middle particle. Now you'll notice here I'm using a lowercase l. I know in this font it's a little hard to see. Normally I would make that with a loop, but oh well, that's the font. All right, so it's a lowercase l, and that's because I'm dealing with a particle and not a rigid object, technically, even though we're looking at it that way. But fancy notation. If you used a capital L, no one's going to bother, right? Questions there? Okay. Part C, what's the total angular momentum of the three particles? Again, not really that hard with what we've already found. If it's a rigid object rotating about a fixed axis, its total angular momentum is just its total rotational inertia times omega. And we already found the total rotational inertia. It was 14 ml squared times omega. So there we go. And so finding the angular momentum of a rigid object rotating about a fixed axis is not that hard, except you got to deal with the angular momentum deal, right? Or sorry, the rotational inertia deal. I don't know why I keep confusing those today. Right? So you have to deal with rotational inertia, and that can get challenging. And of course, you remember we have a bunch of them that we have memorized and we're supposed to be able to derive on an AP test. So here's a second question, okay? Angular momentum is often used when looking at things that are orbiting. Say, for example, here is a planet of mass m, which is orbiting a sun. Just some random mass and some kind of reddish, I don't know, pinkish sun. I don't know why. It's what I chose. Shows up well. All right, so here's a mass, and it's in an elliptical orbit, all right, around that sun. Very elliptical orbit. Way more elliptical than any of the planets in our solar system, but for purposes of being able to see things, makes life easier. I want to know what the angular momentum is. Right? Well, this isn't really a rigid object rotating about a fixed axis. It's a particle. So we'll have to break this down a little bit, okay? But let's start out with our fact that right now it's a distance we will call r away, right, from the planet. It orbits around the planet, so that's our axis of rotation. This mass would be going, let's assume it's rotating around counterclockwise because that's what I did in my diagram. So at this point, its velocity would be right here. Notice I picked a special point. There's only 2 points where this is true, where the velocity is actually tangent, right, to the r, to the distance here, where it's a 90-degree angle. We'll look at what happens when it's not a 90 degree in a moment. Okay, so rotational inertia of a rigid object rotating about a fixed axis is I omega. So what would the rotational inertia of this planet be? Well, it acts like a point particle, right? And a point particle has a rotational inertia, of course, of mr squared. But I did not give you the angular velocity, right? I gave you the linear velocity. But we can convert, right? Because we know v equals omega r. The linear speed of a rotating object, or a point on a rotating object, or in this case, an object rotating about an axis, is the angular velocity times the radius, or omega is v over r. Plug those two things in. We get the angular momentum of this particle, and notice me using the lowercase l, traditional for particles, as opposed to the capital L, traditional for rigid objects rotating about fixed axes. If you just use a capital L all the time, no one's going to say it's wrong, right? But you might see on an AP test little l's as opposed to capital L's. All right. Notice here the r on the bottom cancels out with one of the r squareds. And since these are all multiplied, I can change the order and grouping around, and we end up with RMV. The distance from the axis of rotation to the mass times its speed. So this is the rotational inertia of a particle, right? But notice mv is the linear momentum, right, of the planet. So this is really just r times the linear momentum. Right? It's the linear momentum times an extra r. Kind of like torque is the force times an extra r. Very similar in many ways, torque and angular momentum, especially in the vector algebra we're about to get to. Now, what about if it's not at one of those fancy closest or furthest points which by the way is called perigee and apogee. You're at perihelion and aphelion. Perihelion's when you're closest to the sun. Aphelion is when you're farthest from the sun. What if you're somewhere in between? Well, then that would be R. And your V would be here. And notice that that is not perpendicular anymore. Well, if we think about what we did with torques, couldn't we break this velocity up into perpendicular components? Right, there's R drawn tail to tail with V. And so theta would be the angle in between R and V. Right, if we draw two vectors tail to tail, this is the angle in between. Couldn't we break V up into a component which is radial and a component which is tangential at that point? This is the perpendicular component. See the little perpendicular sign? And a lot like torque, the radial part doesn't have an angular momentum. Why doesn't it have an angular momentum? Well, because this part, if all the object was moving radially, it's not really changing position. It's not orbiting this point. Right? It would either be going directly into the sun or directly away from the sun. And just like with a torque, right, it applies no torque if it's radial. Well, it doesn't really have an angular momentum if it's radial because it's not in rotation. Right? It's always staying in the same orientation. So the part that we need here is the tangential part, right, of this. Okay, so we want RMV tangential, the tangential speed at that point. And if we look at the trig, right, isn't that V sine theta? Right, hypotenuse times the sine of the angle. Right, that's the perpendicular part of V. And that makes the angular momentum of a particle RMV sine theta, where theta is the angle between R and V. RMV sine theta. See how this is a lot like torque, which is RF sine theta? Oh. Well, notice R is a vector. Velocity is a vector. Angular momentum is a vector. So we are multiplying two vectors together, and in the end we are getting a third vector out. A third vector which acts perpendicular to the plane containing the two vectors. I hope that sounds familiar, because in vector algebra, that's a cross product. Remember how we did that with R cross F for a torque? Right? It was the perpendicular part of R and F that created a torque. Right? So same kind of thing here. It's the same vector algebra. Right? So it's R cross MV as a cross product, which is the magnitude of R, the magnitude of MV times the sine of the angle in between. We use the right-hand rule, of course, to figure out the direction. I'll show you that in an example in a minute here. But MV is really just the linear momentum. So we can write this as R cross P if we want to. So this is really the generic equation for a particle, for the angular momentum of a particle about some axis. And you need to define where that axis is so that you can define R. Okay? It's R cross P. How often do you use R cross P? Not very often. Most of the time you use RMV sine theta, unless you're doing three-dimensional unit vector notation, which I'm not even going to bother to run you through because I've never seen it on one of these tests. Right? So almost all the time, if we're dealing with a situation like this planet orbiting the sun at some point other than where the velocities are tangent to the radius, right, of its orbit, we're just going to use RMV sine theta. But the shorthand way is R cross P. Right? And you got to go in that order, remember, because cross products are not commutative. So you rotate R into the momentum, and your outstretched thumb is the direction of the angular momentum. Units? Well, R is in meters, mass is in kilograms, speed is in meters per second. Sine of theta doesn't have units. Put them together. Kilogram meters squared per second. Do you see how that's just momentum units with an extra r, with an extra meter? Right? Kilogram meter per second are momentum units, mass times velocity. And then you got a little extra r in there. So the same units, right? All right. So this angular momentum is a vector whose direction is perpendicular to the plane containing r and v, and you use the right-hand rule. So you rotate r into v. Hopefully you're all putting your hand up there and you're looking at it. If you rotate r, which is this, you got to draw them tail to tail, right? Rotate r into v, and your thumb in this case should be pointing outward, which means we've got a positive angular momentum. It's perpendicular to the plane containing the planet and the sun. This is three-dimensional cross products. Ooh, R cross P for angular momentum of a particle. Okay. And angular momentum is used a lot for orbiting of things that are orbiting the sun, or actually things that are orbiting in general. We tend to use angular momentum to discuss them. Sometimes conservation of energy, but more often angular momentum, right? And we're going to do a lot more of that in the universal gravitation unit with which we end the year. So a little example here. This one's called example 1 for some reason. We have a particle, which we're going to call P, which is right there. It's got a mass of 2 kilograms. And with respect to this axis, which is here for some reason, it is a distance 3 meters from the axis. It has a velocity which acts in this direction, which is 4 meters per second. And there's a force acting on it, which acts in that direction, which is 2 newtons. All 3 vectors lie in the xy plane, which means they lie in the plane of the screen. I want to know 2 things about this object, about the origin. So notice here, I'm saying that we are going to calculate all these things about this point. When you're dealing with a particle, right, you have to have a point around which you think of the thing as orbiting, or rotating, if you will. Okay, so you got to have some axis. If it's a rigid object, it's got a fixed axis, or even a rolling object, right? You know where that axis of rotation is. But in the case of a particle, you've got to apply some sort of coordinate system to some point, right? So I've given you that here. So the first thing I want to know is what's the angular momentum of this particle? So as we just saw, right, the angular momentum of a particle, notice the use of little l, is r cross p, which is r cross mv, which is really r mv sine theta, right, where r is the distance, m is the mass, v is the speed, and theta is the angle between r and v. So let's draw this out. If that's the particle, right, here's r, but we have to draw it tail to tail, so there's v, right, and that's 30 degrees, and there's r. So theta is actually 150 degrees. Now, if we plug 30 degrees in, would we get a wrong answer? Well, if you know trig, you know that the sine of theta is the same as the sine of 180 minus theta. Okay, so in other words, the sine of 150 is the same as the sine of 30. Okay, but there would be another way to do this problem, kind of like we did in the other diagram. Okay, we could draw these tail to tail, and then this is the angle in between, so we should technically use 150 degrees. However, we could use the perpendicular part of the velocity, the part of the velocity that's perpendicular to r, which would be this component right here, and that component would be v sine 30. Oh, see, so sine 30, sine 150, going to be the same thing, right? So r is 3 meters, mass is 2 kilograms, speed is 4 meters per second, sine of 150, which is really the sine of 30, which I am sure you all have memorized as we used to have to do in the old days, it's 0.5. 3 times 2 is 6, times 4 is 24, times a half is 12 kilogram meters squared per second. And This is an angular momentum, which technically needs a direction. Right? On a multiple choice problem, they might say the magnitude of the angular momentum so that you don't have to worry about that. But in this case, I just said angular momentum. So what direction does it act? Well, right-hand rule says rotate R into V. Need to draw them tail to tail, right? Like I have here. So if we rotate R into V, what direction is your thumb pointing? Out of the page. Or if we were doing three-dimensional unit vector notation, positive k cap, right? Different ways you could say it, right? Positive in this case. Now, everybody okay with that? Okay. Just as a callback, let's figure out the torque acting on the particle. After all, I did tell you how much force is acting and how far away from the axis of rotation that force is acting. So you might remember torque is R cross F, or RF sine theta, the magnitude of R, the magnitude of F, and the sine of the angle in between. Well, there's F, there's R, and that's a 30-degree angle. No magic there. It's just, I stole this out of somewhere, and whatever I did, they happened to make those both pretty 30-degree angles. I think so that you didn't really need a calculator. So R is 3 meters. F is 2 newtons. Sine of 30 is, of course, 0.5 again. Right? So this is 3 Newton meters of torque. Again, if you rotate R into F through the smaller angle, right, it's out of the page or positive k cap. Okay, so we didn't do a lot of this with torques, right? And we don't do a lot of this with angular momentums. We tend to do more of this with angular momentums with, again, objects orbiting, like planets orbiting suns and things like that, satellites orbiting planets. But technically, you can define a torque and an angular momentum for an object around any point you want. Right? You just have to treat that as your origin, if you will, and your coordinate system origin, right? And then define R, your position vector, right, for your velocity and your force. And then you can calculate angular momentums and torques.